All right, we're going to talk about the hidden brain behind pretty much everything you use. It's a device that, well, quietly automates our entire world. Let's get into the story of the PLC.
Seriously, think about it. The car you drive, the food in your kitchen, there's this invisible brain making it all happen. And no, it's not magic. It's a small, tough-as-nails computer that completely changed the rules of manufacturing.
Just try to picture a modern factory, right? You've got conveyors, robots, giant presses, all these sensors, and they all have to work together in perfect harmony. We're talking split-second precision. One wrong move could be absolutely disastrous. For decades, this was the exact problem engineers were wrestling with.
And for a very long time, the answer wasn't code or software. Nope. It was a symphony of clicks and clacks. The whole show ran on a device called the electromechanical relay. So, what is a relay? You can basically think of it as a tiny automated light switch. But instead of your finger flipping it, you use a small electrical current to flip a much larger, more powerful switch on or off. It's a really clever way to let a tiny little signal control a huge machine.
So how does it actually work? Well, it's really just basic physics. A small electric current creates a magnetic field, and that field physically pulls a tiny lever to flip a much bigger switch. That's it. And the key thing to remember here is that it has moving parts.
But okay, what happens when you need to make more complex decisions? Something like, if the safety gate is closed and the part is in place, then you can fire the press. To do that, you had to physically wire hundreds, sometimes thousands of these relays together into these enormous cabinets that just looked like a terrifying spaghetti of wires. And this system was an absolute nightmare. The control panels were massive. If you wanted to change the logic, even a little bit, an electrician had to spend days, maybe even weeks, physically rewiring everything. And because these were mechanical switches with moving parts, they were constantly wearing out. Can you imagine trying to find one broken relay in a cabinet of thousands? It was nearly impossible. As factories got more complex, this system was just hitting a wall.
So by the late 1960s, the auto industry was desperate for a better way. They needed something that was solid state, flexible, and totally reliable. What they got was a revolution in a box.
And that's when the Programmable Logic Controller, or PLC, entered the scene. The idea was just brilliant in its simplicity. Take all of that complex physical wiring and just turn it into a computer program. A program that lives inside a single, ruggedized computer built to survive on the factory floor.
The concept itself is pretty straightforward. You've got inputs, like buttons and sensors, sending signals into the PLC. The PLC then runs its program, the logic that used to be that physical wall of relays, and it decides which outputs to activate, like turning on a motor or a warning light.
So suddenly that entire cabinet of clicking relays and tangled wires could be replaced by one compact, silent, and incredibly reliable device. The hardware got a lot simpler, but the real genius, well, that was in the software.
But the inventors of the PLC now faced a new problem. How do you get factory electricians and technicians, who are experts in relay wiring, to adopt a computer? Well, you don't force them to learn computer science. You make the computer speak their language.
And that was the masterstroke. Instead of creating some complex new programming language from scratch, they based it directly on the electrical schematics that engineers and electricians were already using every single day.
And here's the beauty of it. On the left, that's a traditional wiring diagram. On the right, that's the PLC programming language, called ladder logic. They look almost identical, right? Physical wires became virtual lines on a screen. Physical relays became software instructions. An electrician didn't need to learn to code, they already knew how to read this.
Reading it is incredibly intuitive. You just imagine electrical power flowing from this vertical rail on the left, which they call the hot rail. The program itself is made of rungs, just like a ladder.
It's really just a simple four-step process. Power starts on the left. It tries to get across the rung by passing through a series of conditions. These are your inputs. Is a button pressed? Is a sensor tripped? If a complete path is made, power reaches the output coil on the right, and then the corresponding device, a motor, a valve, a light. It just turns on. It's simple, it's visual, and it's so powerful.
This breakthrough didn't just change a few factories. It basically enabled the entire era of modern automation as we know it.
The advantages were just huge. All of a sudden, complex automation was cheaper. You could change manufacturing processes in minutes with a keyboard, not in weeks with a pair of wire cutters. With no moving parts, they almost never failed. And since they were computers, they could handle complex tasks like timing, counting, and math, things relays could never dream of doing.
And that brings us to today.
The PLC is the unsung hero of our daily lives. They run the bottling plants for our drinks, the roller coasters at amusement parks, the HVAC systems in skyscrapers, and yep, even the traffic lights that manage our commutes. They're the invisible brains keeping our world running smoothly.
So the big takeaway here is that we're surrounded by these invisible systems that just work. And now you know that so many of them are powered by a really simple idea: translating the physical language of wires into the flexible world of code. So the next time you see a complex machine working in perfect sync, you'll know to look for that hidden brain inside, speaking the simple, powerful language of ladder logic.